Hello everyone, welcome to our talk. Let me introduce myself. So my name is Masood Rahman. I am an assistant professor from Dalhousie University. This is a collaborative work with Polytechnic Montreal and University of Saskatchewan. So my collaborators are Futscom, so he is a professor from Polytechnic Montreal. Then Shamima Yasmin is a PhD candidate from University of Saskatchewan. And Chanchal Roy is a professor from University of Saskatchewan as well. So this talk is about query reformulation in the context of bug localization. That means we are going to talk about software bugs. Now, software bugs were there from the very beginning of software engineering. But let me give you a bit of recent statistics. So in 2017, more than 600 software bugs were recorded, and these bugs cost the global economy about $1.7 trillion. And those bugs also affected more than 3.7 billion people all over the world. Now, these are obviously big numbers, and the developers also spend like 50% of their programming time to deal with software bugs. Now, the process of finding and fixing software bugs is called a software debugging, and there are three major stages of software debugging. And the very first stage is bug localization. That means in this stage, you need to find the location of the bug within the code base. Then the second stage is bug understanding. So let's say you have identified the location of the bug, but you need to understand the dynamic behavior of the bug using different techniques like bug reproduction. And then once the bug is localized and well understood, then that is the third phase. That means the actual fixing of the bug, or let's say the repair of the code, right? So that's the third stage. Now, the focus of my today's talk is bug localization. That means we'll be talking extensively about how to localize the bug in the code base. Now, if you are hearing the phrase bug localization for the first time, then this example is for you. So let's say we have a bug report, and this bug report is talking about some kind of software bug, but that bug is hidden somewhere within the code base. Now, the process of finding the location of the bug within that code base is called bug localization. Now, in this talk, I am going to focus on a specific type of bug localization called IRbased Bug Localization. That means we will use information retrieval techniques for localizing the bug. Now, if the information retrieval does not ring a bell, think about Google search. So you submit a query, and against that query, you try to find some relevant results, right? So similarly, in the case of information retrieval technique, the bug report is considered as a query to find the buggy code from the code base. Okay, so let me give an example. So what many folks did, they considered this whole bug report as a search query, and then they will submit that query to a code search engine like Lucene, and then the Lucene will return a ranked list of results. So the idea is the buggy code will be within that top position of that ranked list. But you see that this bug report is not designed to be used as a search query. So oftentimes when people use this bug report as a search query, it does not work well in the context of bug localization. So what many folks did, they analyzed the keywords from this bug report, and then they try to come up with a subset of keywords as a search query, and then they will submit that query to the same code search engine to identify the buggy code at the topmost position. Now, I would like to focus on this specific part, that is how can we formulate appropriate queries from the bug report. So that is the focus of my today's talk. So let me give you a bit more examples. So let's say this is a bug report, and this bug report contains lots of structural information like stack traces. Then we have also another type of bug report that does not contain any structural information. So the idea is to construct appropriate search queries from both of these bug reports. So that is the query reformulation phrase comes from, right? So study shows that developers perform badly to identify appropriate search keywords from the bug reports, and about 88% of the times they fail to find appropriate keywords from the bug report. So that is why this is an interesting research problem, and we are going to drill down on this topic of query reformulation in the context of bug localization. So yes, we have divided our study into 3 research questions. So in the first research question, we try to evaluate the query reformulation practices in the IRbased bug localization. So that means we apply the state of the art of query reformulation to bug reports, and then we see whether we can extract appropriate queries from that bug reports or not. So that is the focus of the first research question. And then in the second research question, we investigate whether those bug reports actually contain some optimal search queries or not, right? So the state of the art technique from the first research question might fail to identify appropriate queries. So in the second research question, we basically investigate whether the bug report actually contains some optimal queries or not in the first place. Then in the third research question, we try to differentiate between optimal and non-optimal search queries in terms of their lexical as well as syntactic properties. So these are the 3 research questions. And this is our workflow. So first, we collect thousands of bug reports from the bug tracking system. And then we also collect bug fixing commits from the version control system. And then we try to do the linking between these two. And we also do a lot of filtration. Now, the detailed steps are discussed in the paper. And this is how we come up with our data set for our experiment. And then using this data set, we try to answer the three research questions that we have. And then finally, we come up with some actionable insights. Okay, so let me talk about the experimental setup. So we selected 6 subject systems and we collected more than 200 bug reports from these subject systems. And we use 4 different performance metrics to evaluate the search queries in the context of bug localization. And you might hear this phrase called baseline queries. So when I say baseline queries, that means basically the pre-processed version of the bug report. Now in the bug report, you have title as well as description. So baseline queries basically refer to the pre-processed version of that title and the description from the bug report. Okay, now let's talk about our first research question. So we, from the literature, we found that there are 2 major methodologies for query reformulation. So one is frequency-based and another is graph-based. So let me give you an example. So let's say this is a bug report, and what the frequency-based techniques basically do, they try to find the term frequency as well as the inverse document frequency of all the keywords from a bug report. And then using this TF-IDF, they try to identify the most important keywords, and this is how they construct the search query from the bug report. On the other hand, the graph-based techniques basically convert a bug report into a text graph like this, and then they apply different kind of graph-based techniques, graph-based techniques like PageRank algorithm to identify important nodes from this graph, and then those important nodes will make the query for that particular bug report. So these are the two major techniques, and we selected several representatives from these two different dimensions. And this is the empirical evaluation that we have. So you see, this is the performance for the baseline queries, and these are the performance for the frequency-based techniques, and this is the graph-based techniques. So what you can see is that the baseline query performs pretty well, and the state-of-the-art query reformulation techniques are not able to outperform the baseline query in bug localization. So that is a kind of shocking performance. So this performance can be explained using these statistics as well. So what we found that on average is each baseline query will have like 50 keywords. On the other hand, these state-of-the-art techniques are returning only, let's say, top 10 keywords, right? So that means this guy is achieving quite similar performance to the baseline performance using only 1/5 of the baseline keywords, right? So yeah, so that's a kind of makes sense, but we did further investigation. And what we found is that in our data set, there are some bug reports that can lead to high quality baseline query in the high quality baseline queries by themselves. So that means when we take the bug report and do some kind of pre-processing, that pre-processed version actually lead to pretty high performance. So for example, you see for this, for about 2/3 of our bug reports, we found that those bug reports are leading to pretty high quality baseline queries, and that is why they are achieving like 100% hit at 10. But there are some bug reports in particular, so like 1/3 of our bug reports, for those bug reports, the baseline queries are performing pretty poor. So for example, as you can see, for about 34% of our bug reports, we found that the baseline queries were not able to return any relevant result within the top 10 position, right? So that's an interesting finding. But on the other hand, you see that state-of-the-art technique were able to provide a bit higher performance than the baseline search queries. So this is a kind of interesting findings. And what we can conclude from here is that for 1/3 of the bug reports from our data set, baseline technique is performing very poor, and the performance of the state-of-the-art techniques are a bit better, but not sufficient, right? So this leads to our second research question. And in the second research question, what we try to find out is that whether these bug reports actually contain any optimal search queries or not. And for that, we used a genetic algorithm. And this is how we use genetic algorithms. So first we take a bug report, and then we extract all the individual keywords from that bug report. And then we randomly select certain keywords from that keyword collection to generate our population. Now, if you are familiar with genetic algorithm, you will know that then this population will go through different kind of genetic operation like selection, then crossover, then mutation, and then we'll also calculate the fitness of individual population. So in our case, each individual is basically a set of random keywords. And we used query effectiveness as well as map to determine the fitness of these candidate search queries. And this is obviously an evolutionary process. So that means it will go through multiple iteration and finally will come up with some optimal search query. So let me give an example. So this is a bug report. And when we apply genetic algorithm through this process, we can come up with a optimal search query like this. Okay, so now let me show you the empirical evaluation of the optimal search queries. Okay, so as you see that this is the performance of the baseline search query, and this is the performance for the optimal search query. And it is very interesting because you see these optimal search queries were able to return 87% hit at 1, right? And this is the performance for the whole bug report. So for the whole data set. But we also do the investigation for the subset for which the baseline queries were not able to perform well, right? So you see that the optimal queries were able to provide pretty good performance, whereas the baseline queries basically fail. And this is also true for the another subset for which the baseline technique basically failed, right? So this is very interesting because if we summarize our findings from here, what it tells is that at least 1/3 of the bug reports from our data set for which the baseline queries are very poor and the state-of-the-art techniques were not able to deliver good queries, but in practice, those bug reports actually contain optimal search keywords. But the state-of-the-art techniques were not able to find those optimal keywords, right? So this is very interesting findings. And this leads to our third research question. And in the third research question, we try to differentiate between optimal and non-optimal search queries. And this is the data set that we used. So we collect more than 13,000 bug report, 13,000 search queries. And we did our investigation using around 5,000 optimal search queries and 5,000 non-optimal search queries. So when I say optimal search query, it means that this query can return the relevant result at the topmost position. And when the query cannot return the result within the top 10 position, then we consider that query as non-optimal. And we used, we basically collect different syntactic and lexical properties of both optimal as well as non-optimal search queries. And then we use machine learning techniques to differentiate them, right? So for our classification, we used random forest algorithm, and this is the performance. Now you see that for both optimal and non-optimal search queries, we are able to achieve around 80% precision and recall, which is very interesting. And then we did a bit of feature importance estimation from that random forest model. And what we found is that the optimal queries and the non-optimal queries could be very different in terms of their keyword frequency, then term entropy, then the keyword location, as well as their parts of space. So we did a bit of distribution analysis, and you can see that their density plot is quite different, and the variance is also different. So we performed a statistical significance test, and we found that these properties are significantly different for optimal and non-optimal search queries. So then we selected these 4 different properties, and we did a bit of regression analysis. And what we found is that the term frequency and then the entropy, these are not good indicator of the optimality of a search query. On the other hand, this body keyword ratio and the noun ratio are pretty good indicator of the optimality of a search query. And all these 4 features were found statistically significant in this regression model. So based on these findings, we come up with 4 actionable insights. And what we found is that the optimal keywords are significantly less frequent than the non-optimal keywords in a bug report. Then the optimal keywords are less ambiguous than non-optimal ones. And we use term entropy to determine that. Then we also found that the optimal keywords are more likely to be found in the body section than the non-optimal ones. And then we also found that the optimal keywords are more likely to be nouns than the non-optimal ones. So we apply these actionable insights into our experiment, and we repeat the experiment, and we found that because of these actionable insights, we gain some significant performance improvement. So not only for the baseline queries, but also for the state-of-the-art queries, we are able to achieve significant performance improvement, which is interesting. So guys, this is our take-home messages. So about 1/3 of the bug reports cannot provide high-quality baseline queries, and even the state-of-the-art techniques are not sufficient enough to provide good queries from them. But we demonstrate that using genetic algorithm, we demonstrate that those bug reports actually contain some optimal search queries, and those optimal search queries can lead to very high performance. And we also demonstrate that the optimal keywords and non-optimal keywords are significantly different in terms of their different properties like frequency, term entropy, term location, as well as parts of speech. So our findings has provided these two important open questions. That is, how can we automatically detect the optimal keywords from a bug report? And for this, we will need more sophisticated approaches rather than TF-IDF. And then how can we determine the fitness of a candidate query when we use genetic algorithm? Because in our technique, we use ground truth to determine the fitness, which might not be used in practice, right? So we need a practical fitness function for genetic algorithm-based query reformulation. Okay, guys, thank you for your time. Now, if you guys have any question, please send those questions to this email and we'll be happy to answer. Thank you.